Hello everyone. Till now in this chapter we have understood about Faraday's law of electromagnetic induction and also the Lenz's law which gives the direction of the induced current. And when we discussed the Lenz's law, we have also verified the Lenz's law with the help of conservation of energy. So a qualitative analysis of energy conservation regarding the induced current or the induced EMF was already seen when we discussed the Lenz's law. Here we are going to do a quantitative analysis of the energy conservation. For that, the similar loop that we took to understand the motional EMF is again considered. And here we also mention the resistance of the conductor. The resistance of arm PQ is considered to be R, and we consider that other arms, the remaining 3 arms of this rectangular conductor are negligible when compared to the resistance of the movable arm PQ. So the overall resistance of this rectangular loop is considered to be small r. And now according to Ohm's law we know that the current is given by voltage by resistance, and here the current is due to the induced EMF, and therefore we can write the relation I is equal to E by R, where R is the resistance of this rectangular conductor. And if you remember, the motional EMF that we obtained was given by the expression E is equal to BLV, and substituting this value we can write I to be BLV by R. So the current through the arm PQ is obtained to be BLV by R, and we can see that this is a current carrying conductor and it is placed in the magnetic field. Therefore, it will experience a magnetic force which is given by F is equal to IL cross B, and its maximum value is ILB. And the current through this arm is BLV by R, and substituting that value we can write force here acting on this PQ arm is equal to BLV by R into L into B, which makes this expression to be B square L square V divided by R. So our case is we are having a rectangular conductor which is placed in a uniform magnetic field, and the movable arm PQ is pushed with a velocity V, and we have seen that due to the drift velocity of the electrons in this arm, an induced current is generated, and consequently the current carrying arm PQ, which is in the magnetic field, experiences a magnetic force given by the expression F is equal to B square L square V by R. Now we know that the arm PQ is pushed with a velocity V, and therefore a work is done on this arm, and we know that work done per unit time can be expressed as power, and we know that work is force into distance, and therefore the expression for power we can write it as P is equal to F into V. Now we have the expression for force, and multiplying the force with velocity we can get the power, and therefore the power expression can be written as B square L square V square divided by R. So now we have seen that a mechanical energy here is converted into an electrical energy which is caused by the induced EMF, and if we analyze the joule heat produced here, we can see that joule heat is given by the expression P is equal to I square R, and we have obtained the expression for current I as BLV by R. By putting this value here, we can get the expression for power as B square L square V square by R, which is same as the expression of power due to mechanical energy. So the mechanical energy which gives an electrical energy is then converted into thermal energy. So when we analyze the energy conservation in this whole process, we can see that the mechanical energy is converted into electrical energy, and which is then converted into thermal energy. Now, from this quantitative study of energy conservation, we have an interesting relation which we obtain by analyzing the induced EMF. We know that from Faraday's law, we have the expression for induced EMF. The magnitude of induced EMF can be written as delta phi by delta t. And also from Ohm's law, we can write induced EMF is equal to current into resistance. We know that current is time rate of charge, which can be written as delta Q by delta T, and therefore we obtain, according to Ohm's law, the expression for EMF as delta Q by delta T into R. And if we compare these two expressions of EMF, we can see that delta phi by delta T can be equated to delta Q by delta T into R, and from which we can get the relation delta Q is equal to delta phi B by R. So this is the whole quantitative analysis based on the energy consideration, and we can see the energy transformation here. And also we obtained a relation which is delta Q is equal to delta phi by R. By now we have learnt that a change in magnetic flux can induce current, and we have seen the example using a coil. So we have seen how current is induced in a coil. Now we are going to analyze what happens to a bulk piece of conductor when it is subjected to changing magnetic flux. Now we are going to consider a metallic plate which is oscillating in between of a magnetic field applied. In the case of induced current through a coil, we kept on moving the magnet placed nearby it. But in this case, our magnets are kept stable and we are moving a metallic plate like that of a pendulum in between these magnetic poles. So you can see that we are applying a magnetic field from North Pole to South Pole, and our metallic plate is oscillating in between these poles. So as the metallic plate enters the magnetic field, the flux associated with the metallic plate changes, and definitely that creates a current which is having a swirling pattern like that of eddies in water. And these currents are called eddy current. Eddy currents can be defined as the loops of electrical current induced within the conductor by changing magnetic field in the conductor. So we obtained eddy current by keeping two magnets stationary and by oscillating a bulk conductor through this magnetic field. So when our magnetic plate is entering the field, we know that the flux linked with this conductor is increasing, and therefore according to Lenz's law, the conductor will produce a current in such a way that it opposes the cause for this induced current. So increasing the flux is the reason for the induced current, and therefore the current will have a direction such that it reduces the flux. So as we have already seen before also, here in the similar way, here also the direction of current facing the north pole will be anti-clockwise, so that the magnetic moment here act as a north pole. As you can see, the anti-clockwise direction of current gives the direction of magnetic moment to be coming out of the face. Therefore, this face of the plate will be north pole, and therefore the oscillation will gradually slow down and it will cause a damping, and this is called electromagnetic damping. So the eddy current that is produced in this conductor causes electromagnetic damping, and in a little while it will stop. And we can also see that the same plate, when it comes out of the other end, will change the direction of current in the opposite way. So the directions of the eddy current are opposite when the plate swings into the region between the poles and it swings out of the region. So the eddy current produced in this metallic conductor makes the oscillation damped, and to reduce that we are now going to reduce the eddy current. We know that the magnetic moment is given by the expression m is equal to I into A. So to reduce the effect of magnetic moment, we can depend upon reducing the area of the conductor. Eddy currents are also undesirable because it heats up and it dissipates the energy in the form of heat energy. In order to reduce the area of our conductor, we are going to use a conducting plate with holes or slots so that the eddy current produced within this conductor is reduced. So by using such a conducting plate, we can reduce the eddy current and also the electromagnetic damping, and thus this plate can swing more freely. So one of the methods to reduce the eddy current is to reduce the area of the conducting plate, and also another method is by using lamination on the conducting plate.